This is Daniela Roos, Director of MIT CSAIL and Deputy Dean of Research at the Schwarzman College of Computing. And I'm excited to welcome you to the latest installment of Hot Topics in Computing. Today, we'll be chatting with an important thought leader in technology, and in particular in the area of fake data. And this is Professor Hany Farid. Professor Farid is now on faculty at UC Berkeley, but several years ago, we were colleagues and friends in the computer science department at Dartmouth College. Hany is also a member of the broader MIT community, as he was a postdoc here. And I would like to introduce Hany's postdoc advisor, Professor Ted Adelson, who will introduce our speaker. Ted, take it away, please.
Thanks. So it is my pleasure to introduce Hany Farid. He has the distinction of being one of the few people where you can say he invented his own field, which is digital image forensics. I'm pleased to be able to say I was there when he invented this field, but I had nothing to do with it myself. He was in my lab working on various more traditional image processing topics and human vision and computer vision. And one of the great things about Hany at that time and still today is that he has very diverse interests and skills. He's interested in everything, and that has turned out to be really important for the work he's done. He was, so this is just a little before 2000, 1998 or so. And people were aware that the issue of finding image manipulation and fake images was going to be an important image, but nobody really, an important issue, nobody really knew what to do about it. Hany had some ideas. I encouraged him to pursue them. But when he told me what he was trying to do and how he was going to do it, I explained to him why it wouldn't work. And I cited the relevant theorems and offered counterexamples. But he persisted. And finally, when he demonstrated it worked, I was convinced and I was delighted. And I also saw him give a poster soon thereafter at a conference explaining what he was doing. And a famous professor came to the poster, started with a frown, explained to Hany why it wouldn't work, cited the theorems and the math of why it wouldn't work, and then continued through the poster. And as he continued in the poster, he started smiling until at the end he was saying, wow, that's really cool. And occasionally at the conference, I would go back to Hany's poster and I would watch as the next person go through the same thing, starting with a frown, ending with, oh, wow, that's really cool. And so this is, I think, typified what Hany's done through the years is time and again, through his broad interests and skills and creativity, constantly found ways to do things that everyone thought was impossible and everyone could prove was impossible. He continues to do that today and do it in so many interesting ways. And as we all know, these problems have become really critical today. So it will be very interesting to hear what Hany is working on now. Take it away.
Thanks, Ted. It's great seeing you. And Daniela, wonderful to see you after all these years. I'm only sorry it's not in person. So I'm going to talk a little bit about some of the most recent work that we've been doing. So hopefully you have me in full screen. I think you're in full screen now. And the work I'm going to talk about for most of the talk is that of Shuchi Agarwal, who's a really terrific Ph.D. student in my lab, graduating next year. She's going to be on the job market soon, so everybody should pay attention. She is really, really wonderful. We're going to talk about deepfake videos. You may have heard this term. I'll define it for you in a minute. But let me just start with the obvious, and where Ted sort of started is that image manipulation is not new. I mean, as long as we've been taking photographs, well, we've been manipulating photographs. This, of course, is a photograph of Stalin. The gentleman to Stalin's left had fallen out of favor, and Stalin apparently thought that he could just wipe this person out of history by airbrushing him out of the photo. And so how do they do this? Well, this is obviously pre-digital, and so this is done in a darkroom. You take the negative and you literally paint over, and then you re-image, and you can alter a photograph. And one of the questions you might, and Stalin wasn't alone, by the way. You can look throughout history, you see evidence of photo manipulation. And one of the interesting questions you want to ask yourself is, well, why? Why did Stalin go to the trouble? Why not just knock the guy off and be done with it? And I posit that it's because people like Stalin understood the power of photography. They understood the power of visual imagery, which is that if you can change images, you can change history. And while the underlying techniques for manipulating images have changed dramatically over the decades, that fundamental concept that there is power in visual imagery, I don't think has changed. Now, fast forward to the digital age, and we can do lots of fun things with digital images and things like Photoshop. So relatively easy to create the photo like this, where Trump's face was spliced onto the body of a child that former President Obama is holding. And we've been able probably to do this for about 10, 15, 20 years. And as Ted was saying, when I was working with Ted, two, by the way, of the best years of my career, you know, Photoshop was really in its infancy. Film still dominated the landscape. And I remember Ted and I sitting in his office looking at a graph showing the sales of film cameras and digital cameras. And just around the time in the late 90s, early 2000s was the tipping point. It was at the 50% mark where film was on the way down and digital was on the way up. And that's when I started thinking about, well, what happens when we enter a landscape and everything is digital and you can start manipulating digital media? And that sort of led on to a 2-decade question of authenticating digital media. And what happened over that 2 decade is, for the first decade or so, it was really digital cameras, Photoshop, and things like this. And Ted, I remember talking to Ted about this many years ago, maybe 5 years ago, and Ted was saying, you know, this is a great little field. It's a niche field, and you know, it's important. But it was small, and it was true. But something weird has happened over the last 5 years with the misinformation apocalypse that is the internet now, and the role of fake images and fake videos and fake content. And suddenly what seemed to be a relatively small field has become much, much larger. And we'll talk a little bit more about where I see that in the coming years. But in particular, what has happened most recently in the last few years is that we have gone from manipulating things in the darkroom to simple manipulations in Photoshop to full-blown synthesis using advances in machine learning and big data. So we're going to talk about this in particular. So if you navigate to thispersondoesnotexist.com, you will be presented with a single image of a person. These are 6 images that I grabbed off of that website. And these are people who don't exist. They are completely full-blown synthesized by deep learning, in particular generative adversarial network, which I'll talk about in more detail in a minute. Unlike CGI, unlike computer generated imagery where you have a 3D model and a virtual camera and virtual light and texture and hair and highly, highly detailed, that's not this. This is a purely data-driven, image-based technique for synthesizing images of people who don't exist. And that idea of computer synthesizing images or video or audio is what is broadly called deepfake. So let's talk about how these are made very quickly. It's a pretty simple idea. Your job is to generate an image with a face of a person who doesn't exist. And the way that we do that is we have a generator. The generator's job is to create an image. They start by generating a random image, slap down a bunch of pixels on whatever resolution you want. Hand that image over to a discriminator. That discriminator has access to a bunch of faces of actual people, scraped from the internet, some database, whatever it is. And the discriminator's job is to ask, can I discriminate this image handed by the generator from these images that are known to be real people? And of course, that would be a trivial task to do in this case, because that's a bunch of random pixels. Loops back to the generator, says, nope, it's not a person, keep trying again. And eventually, after enough iterations, the generator will eventually make an image of a person. That person will be sent to the discriminator, and the discriminator will say, yep, looks like a person. Yeah. So StyleGAN 2, other techniques for doing this. And they create highly realistic images of people. And now we're even starting to have control where you can play with the gender and the race and the age and the features on it. So it's not just a random person, but you start to have some controls on it the way you would in a CGI world. Now, that's one type of deepfake, a static image. We'll talk a little bit about where that type of technology is being weaponized. But let's talk a little bit, because that's what the bulk of the work we're going to talk about is our deepfake videos, is a deepfake video. So now imagine taking that same generative adversarial network, generative because you're building something, adversarial because you're pitting these two systems against each other. And of course, underneath each of these is a deep neural network. So now imagine we're going to do something a little bit different. We're going to take this image of Jennifer Lawrence, the performer, and we want to change her face to be that of Steve Buscemi. Why Steve Buscemi? I mean, why not? You know, just anybody it could have been. So now what we're going to do is the following. This generator has to change her identity to his identity, and it does it by modifying some pixels, handing it to the discriminator. The discriminator says, can I discriminate that person from the actor Steve Buscemi while keeping the appearance of the image the same? So his head should be down and to the left, his eyes should be slightly closed, the appearance of the lighting and the texture should be the same. All I want to do is change identity. And again, you do this in a very tight loop. And if you do that over and over again, frame after frame after frame, you get something that looks like this. So original video is here. A face swap deepfake is here, where Steve Buscemi has been mapped onto Jennifer Lawrence's face. There's actually an audio track here. I've just taken it out so I can talk over it. So a couple of things. First of all, who would have guessed that Steve Buscemi is such a good-looking woman? I mean, it looks fantastic here. And notice how seamless this is. The lighting looks really good, the expression looks really good, the head movements, everything is moving, and just on every single frame, all that has been done is we've done a face swap deepfake frame after frame after frame after frame. By the way, if you haven't seen some of these, there are really good examples on YouTube. My favorite one just came out a few weeks ago. It's Sylvester Stallone and Arnold Schwarzenegger have been spliced into the movie Step Brothers, and it is very funny and very well done. Slightly not safe for work, but very well done. So this is one type of deep fake where we've replaced a person's face, typically from the eyebrows to the chin, from one face to another. There are two others. Let me just mention them briefly because I'll talk about them later. There is a puppet master deep fake. So here what we do is we take a single image of a person, and then I am the puppet master. So as I sit in front of the camera and move my eyebrows and turn my head and smile and talk, it animates that single image. Yeah, some beautiful work coming out of the University of Southern California from Hao Lee's group on doing that. A lip sync deepfake is slightly different. Here, we take an original video and we have a new audio stream, either synthesized or just an impersonator. And all that's resynthesized is the mouth to be consistent with a new audio track. So whether it's the mouth, the entire head, or just the face, each of these deep fakes, what are we doing? We're trying to make somebody say and do something that they didn't, right? Either for comedic purposes, to interfere with the democracy, or to commit large-scale fraud by getting Mark Zuckerberg to say that his profits are down by 20% and trying to move the stock market. Yeah. So where are we seeing, before I talk, so the game we play here is we don't create these things, we want to detect them. And why do we want to detect them? Well, because we think that these can be weaponized. So where are we currently seeing weaponization of deepfakes? Single, I don't think it will shock you, sadly, single most common use of deepfakes is in the creation of non-consensual pornography. A woman's likeness is superimposed into sexually explicit material, and then that material is distributed online. This is probably the most common form of it, and in fact, it is where the term deepfake came from. Deepfake is the handle name of a Reddit user who used this technology to create the first non-consensual pornography. Big problem for performers, famous people, but also a problem for journalists, human rights activists, people who simply attract unwanted attention. There have been examples, very high profile cases of very powerful women who have tried to speak truth to power and have been harassed with this type of content. It is awful, and many of the big platforms have not figured out or are not willing to figure out how to contend with that. We are all living through highly complex and intricate misinformation campaigns meant to sow civil unrest, meant to interfere with democratic elections for the purposes of trolling or for fraud. And these types of images and video are simply adding fuel to that fire. So, for example, my favorite example of the use of a face synthesized using "this person does not exist" was last year. 17-year-old kid in Florida was bored during his holiday break, and he created a fictional candidate for Congress in Rhode Island. He got that candidate approved by the election board and got an approved Twitter account using a face of the candidate that was synthesized using "this person does not exist." He created a completely fictional character that, as far as anybody knew, actually existed. We've seen these types of faces being used in misinformation campaigns to create fictional profiles on Facebook, on LinkedIn, and on Twitter to create credibility as people create fraudulent accounts. There are entire websites now, by the way, where you can pay somebody $1.99 to create any type of face that you want, or you can just download it for free from "this person does not exist." As Ted will tell you, I got into this business because I was worried about the courts. So 20 years ago, we didn't have the internet that we have today. We didn't have non-consensual pornography. We didn't have even the concept of fake news the way we do today. But we were worried about how we introduce digital evidence into a court of law. And this creates a big problem for how do we trust the digital evidence, whether it's an image, an audio recording, or a video being introduced into a court of law. Obviously, on the national security scale, we are constantly on a daily basis being inundated with visual imagery from around the world in places that we can't physically be. And we have to make things that have huge impacts on the world around us. How do we do that when we don't know if we can trust the visual imagery that we see? Fraud, I've already mentioned it. I create a video of Jeff Bezos saying Amazon stocks are down 10%, profits are down 10%. How long do you think it'll take me to move the market a few $billion before anybody figures out that that video is fake? We've already seen the first example of this. A CEO was lost $250 million or 250 million euros because somebody had created a synthetic voice over a phone call saying, wire this amount of money per this person's approval. They wired the money, $250,000 was lost from a synthetic voice. So all of these things are either here today or we are probably going to be seeing them in the coming years. And this gives us a little bit of concern for how these types of deep fakes can be weaponized. And this is what we want to think a little bit about, is how do we detect these? Okay, so I'm going to talk about some of the work that Shruti has been doing on this front, just one of the techniques that we've been developing. So I'm going to show you in the next slide a series of clips of former President Obama. They're just short little 2 to 3 second clips from his weekly address. I've ripped out the audio just so I can talk over it. So you're going to see a little clip after a little clip after a little clip. And on each one of those clips, he's saying, "Hi, everybody. Hi, everybody." It's the very beginning of his weekly address. See if you notice anything during the clips. So every one of these, again, he's saying, "Hi, everybody. Hi, everybody. Hi, everybody. Hi, everybody. Hey, everybody." Okay, so those are all distinct clips. I could have done that for another 20 minutes or so. And I don't know if you noticed it, but every time he did it, there's this little tilt of the head up into the back, right? And you can see it here. He's coming down. So every time he says, "Hi, everybody," he says, "Hi, everybody." And you can see it right here on that slide. He purses his lips ever so slightly, and then he starts talking. Almost every single weekly address, he starts exactly the same way. When Shruti first showed me this is actually a small version of the longer version. I was sure she had duplicate in it because it didn't seem like they could have all been distinct. Those are all distinct little videos. So what is that? It's a little behavioral mannerism. It's a little tick. Yeah. I have mine, by the way. I've been doing a lot of Zoom talks. So I've been noticing them, how I raise my eyebrows when I emphasize. I tend to move forward when I want to emphasize something. President Obama does this thing where he does, when he says, "Hey, everybody," he does this. He has other ones. Let me give you an example of that. Here's my favorite one. So what I'm showing you here is one frame from an authentic Obama video. And on this graph, what I'm showing you along the horizontal axis is time. This is about 10 seconds. So roughly, let's call it 250 frames or so. And in blue, I'm plotting how much Obama is rotating his head around the horizontal axis as if in the affirmative, nodding in the affirmative. Yeah, that's the blue graph curve right there. The orange curve is how much he is frowning. So the sides of his mouth are turning downward. Yeah. And this is averaged over an hour or so of video. And what do you notice? They're correlated. Yeah. So Obama has this interesting mannerisms, and you can see it now when you go back and watch some of his speeches, that when he delivers bad news, when he's angry, when he's sad, when he's upset, he does this. And he frowns, and there's a slight tilting of the head downward when he speaks. Yeah, it's very consistent, and it's a very interesting, again, behavioral mannerism. Why do I care about behavioral mannerisms? We'll get to that in a minute. Okay. But now let's think about a lip sync deepfake. So what was a lip sync deepfake? I replaced his mouth with a new mouth that has been synthesized saying something else, while his head was saying, well, whatever it was saying in the original video. Same thing, time on the horizontal axis, 10 seconds. Blue is rotation of the head up and down. Orange is frowning. What's wrong here? They're decoupled. Why? Well, because the head was saying what the head was saying in the original video. But the mouth is saying, well, whatever the mouth is saying in the synthesized audio. And although it looks all fine, the mouth is doing what it should be doing and the head is sort of doing something, I've created this chimera of sorts. It's not, the head doesn't know what the mouth is doing and the mouth doesn't know what the head is doing, and I've disrupted that behavioral mannerism. Now, that's Obama's. Yeah, this guy has a different behavioral mannerism. Okay, so same thing, time, 10 seconds. In blue now is this chin pucker that Trump does. I actually can't do it very well. I don't know how he does it. He does this weird thing with his chin if you've seen him talk. And the orange going up here is this, this thing he does with his mouth when he talks. Yeah. And what do you notice here is that they're decorrelated. So when he chin puckers, his mouth is closed. When his mouth is open, he doesn't chin pucker, right? They're decorrelated. All right, Alec Baldwin doing Trump in Saturday Night Live. We created a face swap deep fake. So that's Trump's face slapped onto Alec Baldwin. Yeah. What's going on with Alec Baldwin? So he's got like the individual characteristics of Trump, right? This in the mouth, but he correlates them. Yeah. So he's got that sort of caricature of Trump, but he didn't get the dynamics right or the correlation right. And so what we're going to do is we're going to explore various people, Obama, Trump, Harris, Biden, Warren, pick your favorite candidate, senator, president, prime minister, CEO, whomever it is. And we're going to learn what their mannerisms are. And we're going to try to use that to distinguish them from impersonators. So fundamentally, we're not really going after deep fakes. What I'm going after is whether it's a face swap, whether it's a lip sync, whether it's a puppet master, it's an impersonator. It is whoever is doing these actions. Either you've disrupted the natural dynamics of the head, the mouth, the expressions, or it's just not them. It's somebody else driving the mannerisms. Okay. So here's what we're going to do. I think I've already said that with the lip sync deepfake, you disrupt what the mouth and the head are doing. They don't know about each other. And for the face swap and the puppet master, it's somebody else moving. It's somebody else's mannerisms, even if it looks like somebody else. And we're going to use that. We're going to try to exploit that as a soft biometric to distinguish real from fake. So here's what we're going to do. Take a video, do standard face tracking. So here, the blue box gives me 3D orientation. The red dots that you see around the face give me facial features from which I will extract 18 so-called action units. So these tell me, are you lifting your eyebrows? Are you frowning? Are you smiling? So these various standard action units. So for every moment in time, as I'm tracking that video over a 10-second window, roughly 250 frames, I extract these 18 action units and 2 head rotations. Rotation like this and rotation like this. We ignore this rotation around the vertical axis because politicians do this a lot, and as they're scanning the audience, and it's not diagnostic. Yeah. Okay, so we have 20 measurements that we make. That gives us 20 choose 2, 20 times 19 divided by 2, 190 pairs of expressions and head movements, similar to what I showed you for Trump, similar to what I showed you for Obama. Just look at the correlation or anti-correlation of facial expressions. Okay, so every 10-second clip, I look at 190 correlations and I get a single number out for each of those 190 correlations. So every 10-second clip is now a point in 190 dimensional space, which of course we can't visualize. I'm going to slam that into this 2-dimensional space here. And every data point here is a 10-second video clip for Kamala Harris, Hillary Clinton, Elizabeth Warren, Bernie Sanders, et cetera, et cetera. So this work was obviously done during the Democratic primary. What do you notice? Oh, by the way, these all these ones scattered in here, these are random people taken from something called the Face Forensic Database. It was part of a larger testing that we were doing. So you can ignore those. But these clumps that you see here are all individuals. Even in this 2-dimensional space, this is an originally 190-dimensional space, you see this very nice tight clustering. So Kamala Harris, all the videos cluster together. Obama, O'Rourke, Booker, Trump, Sanders, Warren, et cetera. So how do we exploit this? So what does it tell us, by the way, is that people are pretty consistent and they're distinct from each other. We found this, if you will, soft biometric. And I say soft because I don't think I'm going to distinguish Kamala Harris from 7 billion people in the world, but I don't have to. I just have to distinguish her from an impersonator. So here's what we're going to do. We do this in the full 190-dimensional space, but we can visualize it here. We build a simple 1-class nonlinear support vector machine, nothing fancy, no neural nets, nothing complicated here. So we have a bounding surface around the authentic Obama videos. And then any 10-second clip, face track, extract action units and head movements, 190 correlations, put a point into the space, and are you within the bounding surface or not? If yes, authentic. If not, not authentic. And notice, by the way, these data points are the deepfake Obama. They're close, but they're outside. And if you're outside of here, it's not that you're a deepfake. It's just that you're not Obama. But that's all I care about. If I'm looking at a video and it looks like Obama, I just want to know, are the behavioral mannerisms, are the temporal dynamics unfolding over a 10-second window consistent with the mannerisms of Obama or Harris or Clinton or whomever. Okay, so let me show you how this, some large-scale testing. So we have a number of different data sets. I'll give you specific numbers in a minute. Original Obama, super easy to get. Just go on YouTube and scrape YouTube. You can get hours and hours and hours of video of Obama. We had some colleagues and friends up at the University of Washington create some lip sync deep fakes of Obama. So now just the mouth has been replaced with a new audio track. There's a very good impersonator on YouTube of Obama. This is not a deep fake. It's just somebody pretending to be Obama. He's very funny. From that, our friends at the University of Southern California, Hao Li and his group created face swap deep fakes, where we swapped Obama's face onto the impersonator's video. And they did that. And then also the USC group made a bunch of puppet master deep fakes, where one of the graduate students in Hao's lab was just sitting in front of the camera animating Obama. So we have 1, 2, 3 deep fakes. Those are the 3 that I enumerated earlier. We just have an impersonator, because if we can detect the differences, it doesn't matter whether it's just a real video, but it's somebody who's not Obama, or it is in fact a deep fake. And then of course we have the authentic videos. All right, so here's how I'm going to show you the results. I'm going to ask, what is the ability to distinguish authentic Obama videos, of which there's about 207,000 10-second clips, from random people? These are primarily newscasters, the comedic impersonator that I just showed you earlier, and the 3 types of deep fakes. The numbers under each of these are the number of 10-second video clips that we're going to try to categorize. Again, I don't have to learn using this data. This is pure testing data. I train on this data, authentic, and it's a 1-class support vector machine. So anything that falls out is not Obama, whether it's a random person, a comedic impersonator, or a deep fake. I'm going to present the results as area under the curve. 0.5 means I'm a chance. I'm guessing whether it's real or fake. 1.0 means I've got it perfectly, a perfect classifier. All right, let's see how we did. Okay, so for random people, comedic impersonators, face swap, and puppet master, we're roughly an AUC of 0.95. Yeah, so that's pretty good. Not perfect, but pretty good. On a single 10-second clip, by the way, that's actually not bad. That's all I'm working on is a 10-second clip. We took a big hit here. We're at around a little bit above 0.8 on lip sync. Why is that, by the way? Does that make sense? So first of all, sure. What's the nature of a lip sync deepfake? Is all I've done is replace the mouth. The rest of the head is authentic. So how he's moving his head and his eyebrows is Obama. And so, in fact, most of the mannerisms here are perfectly fine. So it makes sense that with these deepfakes, and for people who are not Obama, we should do better, but here we do worse. I won't show you the slide for that, but if we're careful on the features that we use, always using one action unit from the mouth and another from the head, this can bump up to about 0.95. So we just have to be, if we're a little careful, we can get a bump here. But we can also get a bump if we just consider that most videos that we see are typically 2 to 3 minutes. And so if we just simply integrate over all of the 10-second clips in a video, just averaging, you can see you get this nice bump in the dark, I don't know what color that is, blue, let's call it. So here with the Puppet Master, we have just about a 1.0. We got a nice bump on the lip sync to above 0.9. And now we're getting really close to perfect classification, distinguishing only using these behavioral mannerisms over an average of a 2 to 3 minute video, 2.5 minute video rather, of Obama. Now, that's for Obama, of course. I will tell you, I don't have the slide for this apparently, is that we've done this for Hillary Clinton, we've done it for Kamala Harris, we've done it for Joe Biden, we've done it for Bernie Sanders, we've done it for Donald Trump, and the accuracies are all almost exactly the same. There's almost no difference, except one exception. We're really, really good at detecting Elizabeth Warren fakes. And the reason is she is so incredibly animated. If you've ever seen her talk, you are all from Massachusetts. She is just really super animated and nobody can reproduce that animation. So we do really, really well on Elizabeth Warren, slightly better than everybody else. So this generalizes to various people. It's not just an Obama classifier. Now, I'm aware that we are living through a machine learning revolution, or I should say the third machine learning revolution. And I understand that it's very popular to throw machine learning at problems. I think it's really nice to understand what it is that we've learned. And so it's nice that we can look at this and say, look, we've learned this behavioral mannerism that has to do with how people move, for example, their head and their mouth. And for each individual, I can tell you what it is. I can go in and look and see what are the features that are most diagnostic. So for Elizabeth Warren, it's the head movement left and right as she talks. Of course it is. And for Trump, it's something else. And for Obama, it's something else. I'm also aware that we've handcrafted these features. We have by hand selected things that is almost certainly not optimal. But learning what we've learned now, let's see if we can do a little bit better by throwing some machine learning at it. So let me tell you a little bit about what we did following on that initial investigation where we got this idea that we could use these behavioral mannerisms to detect impersonators and deepfakes. So here's what we're going to do to try to tidy this up a little bit and eke out a little bit more performance. We're going to start with FabNet. So FabNet is a deep neural network that captures the appearance of people. And basically what it does, it takes a single image and it extracts a 256-dimensional vector that represents a person's appearance. Okay. Now we care about time. So we're going to, here I'm going to have t equals 1 to 100. So that's 100 frames now. So we've reduced it down to about 4 seconds from the original 10. We did that primarily for computational considerations because once you start doing everything with neural networks, it gets a little more tedious. So we're now only working on 4-second video clips, 24 frames a second, 100 frames. Each one of these gets shoved through a FabNet. Okay. What does FabNet do? This representation right here, this 256-dimensional vector, is a representation of a person's appearance so that if you do a query against a database of faces using that representation, you will get things that have a similar appearance. So for example, here in the middle row, this woman is, her lips are slightly pursed, she's looking directly at the camera and her eyes are closed. The nearest neighbors that you see to the right here using that representation are, well, people who sort of look the same, but it's not the same person, most importantly. Here, for example, the person that's slight profile, and you get nearest neighbors are people similarly profiled, but different identity. That's the whole point of FabNet, is that you are capturing some characteristic that embodies the appearance of the image. Okay? So that's not exactly what we want, but it's a step in the right direction of what we want. So what we do is we take each frame across 4 seconds, we shove them into FabNet, and we get this 256-dimensional representation. Now, what do we want to do? We want to capture behavioral mannerism. So we really want time in there. So that FabNet is one step. Why? Well, if my head is turned this way and I'm frowning, that's an appearance. But then what happens in the next frame? I start to smile. Okay, so I want to capture that change in appearance over time, but I also care about identity. So here's what we're going to do. take the 100 frames, each one goes through FabNet, you get a 256 dimensional representation. Pack that into a matrix. So now it's 100 by 256, okay? That's this step right here. We're gonna shove that representation into something that we built called BehaviorNet. So that's that little green box right there. And out of that comes 512 dimensional vectors. I'm not going to talk about all the nitty gritty details about this. I will give a link at the end of the talk with a paper that describes this. A couple of quick things. This is a standard architecture using ResNet 101. We use a metric learning objective function and a VoxCeleb2 data set. And what we were trying to do was the following. The objective here was to do the following. Given not just a single image, but 100 images, 4-second clip, we wanted to find similar clips in terms of identity and appearance. So for example, here, and that little video clip, you can now see the rock is moving and each person moving. There's 100 frames. Out of those 100 frames, we push them into FabNet, we push them into our BehaviorNet, and now comes a 512 dimensional representation. We then look for the nearest neighbor in the big data set of videos and images that we have, and we extract the most similar. And now you see something really interesting. You see, first of all, it finds the same person, and the thing that they are doing is similar. So here's the rock at slight profile talking. Here's this guy, he starts talking and he turns his head. The nearest neighbors do the same thing. Same thing on this one. This woman's talking and then she turns her head slightly. Nearest neighbors do the same thing. So the output of the BehaviorNet is now capturing two things, identity and behavior. Well, that's what we want. So instead of hardwiring the action units in the head movements, we're now going to use that learned representation from BehaviorNet. And I'm simply using this visualization to tell you that that BehaviorNet seems to have learned a representation that captures both identity and behavior mannerisms. All right. So that's one pipeline. Everybody goes into FabNet, into blue. FabNet goes into this BehaviorNet, that little box there. It could be a whole nother talk talking about how we did that, but I'll ignore it for now. 512 representation, that captures the underlying behavioral mannerisms. Let me just describe another pipeline because we're going to combine a few things in the end. Each of these images is then shoved into a VGG, which is a standard face recognition. Out of that comes a 4096 dimensional representation, which you can just use for face recognition. There's nothing special about VGG. We just use some off-the-shelf representation for face recognition. We get 100 of those for each of the frames of the video. We simply do an average. Why? Well, because we expect the face to have the same identity. So out of this pipeline in orange comes identity. Spatial static identity based on face recognition. Out of this pipeline comes behavioral identity having to do with the mannerisms evolving over time. And now what we want to do is we have a reference set of authentic videos where we know what who it is, we know what the mannerisms are, and we simply ask a very simple question. For this sequence, there is an identity match based on the face. This is Kamala Harris. We have a match based on the behavioral mannerism. Who is the closest in terms of the mannerism of this? And then we simply ask, well, is it the same person? So does the mannerism match the face? And if the answer is yes, it's authentic. And if the answer is no, well, then we say, okay, it looks like Kamala Harris, but it's not moving like Kamala Harris. Mismatch, it's a fake. So that's what we're going to do. Now, let me just show you the evaluation. So we had a couple of different data sets. What I'm plotting on here are 1, 2, 3, 4, 5 data sets in terms of the number of identities in the data set and the average duration of the video. This is the data set that we created that I was just talking to you about. WLDR stands for World Leaders. There's only 10 identities, but we have 14,000 seconds of per identity. So we have really long sequences per person. This is the face forensic database, which has 10,000 people, but only 19 seconds per person. And then there's a few data sets in between that are somewhere in between. And we're going to evaluate the BehaviorNet that I just described across all of these data sets. This time I'm going to present the results in a slightly different way. This is the average accuracy across all 5 data sets. Along here is a parameter, it's just a threshold that allows us to know when we should make a decision. And this is the percent correct. I fear that this might be a little small. 100% is at the top, 0% is at the bottom. Crossover point is roughly 97% across all the data sets. So you can see here 97, 99, 98, oops, 88, I'll get back to that in a minute, and 93. So you can see the crossover for real in purple and fake in green are in the high 90s. I don't have a slide, I'm sorry, to do a comparison to the original technique, but I will tell you we get a 5 to 10% bump relative to the handcrafted features. Not as much as you would have expected, by the way. I expected that the machine learning would have learned a much more diagnostic and representative feature, but in fact, it's a relatively modest bump after all of that work. Now, we took a really big hit here. We went from the high 90s to the high 80s. And why is that? What is it about this data set? And I like this plot a lot because it's a cautionary tale when you're using these big data sets that you download from the internet. So this is one example from the data set, the DFDC data set, which was built by the folks at Facebook. This is, so these were meant to be face swap deepfakes. This is one frame of the source video and one frame of the target video. And this is the corresponding frame of the face swap. Now, what this should have been is this person's identity mapped onto that person's mannerisms. But that's not what happened. All this is a blurry version of this person. And so this face swap is in fact not this person's identity. It's still this person's blurry identity. And so in fact, this database is riddled with some problems where the face swaps just failed. And because there's thousands and thousands of them and the quality control wasn't done very carefully, they're out there. And so when you're evaluating against these, you have to go back and look at your mistakes. And it turned out the data set was actually not very good. And if we eliminate all these, we get back into the high 90s again, just a little bit of a cautionary tale. Okay, so that's one technique that Shruti and I have been working on. Let me talk a little bit about going forward, what's next. So what are the challenges in this space? I think everybody here probably knows that really rapid, startlingly rapid advances in deep learning. So every 3 to 4 months, frankly, every time there's a conference deadline, we see new advances in the synthesis of fake images, fake video, fake audio. So it's a very, very fast landscape. The problem is not, of course, just creating fake content. It's the fact that that content can get online and spread at a speed that is unprecedented because of social media. So if the problem was just we can create fake content, but we have no way of distributing it to the world instantaneously, well, okay, it'd still be a problem. But this is the biggest problem, which is that once this stuff is out there, once the non-consensual porn, once the misinformation, once the fraudulent content gets out there, it is very, very, very difficult to rein it back in. And that's a huge challenge for us working in this space. We have a particularly polarized public that when videos come out, people want to believe that they're fake. So for example, when George Floyd was killed by a police officer, people claimed that it was a deepfake video because they didn't want to believe it. When the video of Speaker Pelosi came out purportedly showing her drunk, people wanted to believe that she was drunk, despite the fact that it was fake. And so when you have a highly polarized public, you can very easily play into people's preconceived notions. And this stuff works because people want to believe it. The biggest threat here, I would argue, is what is called the liar's dividend. So this is a lovely description from Danielle Citrin of what happens when you enter a world where any image, any video, any audio, any news story can be fake. Well, then nothing has to be real. Anybody can simply dismiss something as inconvenient truth. Here, by the way, is how fast the world has changed. Rewind with me, if you will, to 2015. Then candidate Trump gets caught on an Access Hollywood tape saying some very, very bad things about women. Yeah, what did he do? He apologized. He actually said the words, "I am sorry, that was wrong, it's not who I am today." 2 years later, 2017 now, reporter asked him about the Access Hollywood tape. You know what he said? It's fake. One swipe of the hand, gone. Right? That's how fast the landscape has shifted in people's ability to say, you can't believe anything. Whether it's the New York Times because they're too liberal, whether it's Fox News because they're too conservative, or whether the facts simply don't conform to your worldview about the number of deaths of COVID, about humanitarian crisis around the world, about climate change, about any of a number of things happening on the world. You don't have to believe it if you don't want to, because once everything can be fake, nothing has to be real. I would argue that is by far the biggest threat that is emerging on the landscape. Ted knows this very well because Ted and I have talked about this many times, is this is an arms race. You know, we do a little bit something, you do a little bit something, and the game keeps going, and we never quite end this game, like everything else in cybersecurity. So it's both fast paced and never ending. What are the interventions? Well, I think that the YouTubes and the Facebooks and the TikToks and the Twitters of the world have to start taking more responsibility for the mess that they have created in society. They have to stop standing behind, we're simply the platform, we are the wire, we're not responsible. I don't think anybody believes that anymore. We have to find a balance between dealing with the misinformation apocalypse that is among us and having the free and open internet that we all want to exchange ideas. I think as we are talking about regulation, which is happening here on Capitol Hill, it's happening in Brussels, it's happening in the UK, it's happening all over the world, I would argue that we should spend more time talking about the recommendation algorithms and less time talking about the content. The fact is that the reason we have the problem today is not because you can create fake content, not because you can post that, but because the underlying recommendation algorithms favor the most outrageous, divisive, hateful, conspiratorial content because it's good for business. Hate and outrage sells. It keeps people engaged. Engagement keeps you clicking. Clicking is good for revenue. We should be talking about recommendation algorithms more than we should be talking about the underlying content. Obviously, we need to be talking about technological interventions, and obviously we need to be talking about how do you educate the next generation of young minds on how to be better digital citizens and consume trusted information online. This is Shruti Agarwal, really, really wonderful PhD student who's done all the work that I've described and many other really beautiful things in the general space of digital forensics. Let me just touch on a few things happening in the lab, just to give you a flavor for some of the other things that we are working on. Sophie Nightingale is a former postdoc. She just started a job yesterday, in fact, at the University of Lancaster in the UK as a professor. Sophie has been doing some very nice work over the last 2 years on forensic identification, how we identify people from crime scenes. She wrote a really beautiful paper in the Proceedings of the National Academy of Science this year, showing that a technique used by the FBI in actual cases over the last few years, trying to identify people from the wear and tear on blue jeans, is highly unreliable, despite the fact that the courts have adopted it. And more generally, we are interested in how these various digital forensic techniques are being used to identify people, whether it's based on things like clothing, or as Nirja is working on, even simple things like estimating people's height and weight from a single photograph turn out to be highly unreliable. So we have a big emphasis in the lab, not just on whether things are real or fake, but on how you can extract reliable information in a forensic setting to identify individuals. 1/4 of wrongful convictions in this country are due to flawed forensic science, both physical and digital. That field is a bit of a mess, and Sophie and Nirja and I are trying to understand what the landscape looks like, figure out what are the techniques that are reliable, what are not, and how to make them more reliable. Julia Dressel was an undergraduate with me at Dartmouth College, and this work is now a few years old, but I wanted to mention it because it's also in the general space of criminal justice. Julia did a really beautiful undergraduate thesis in understanding the use of predictive algorithms in predicting recidivism that are being used in the courts today, both here in the US and abroad, and how these algorithms have a serious racial bias, and understanding where that bias is coming from and when and if it can actually be corrected. And there's some really nice work in a Science Advances paper that Julia wrote a couple years ago. Everything that I've talked about, Shruti's work on the digital forensics, Sophie's work and Nirja's work on the forensic science, and Julia's work on algorithms can all be found at that website, farid.berkeley.edu. And I think with that, I'll stop. Thanks very much.
Thank you very much, Hany. That was really wonderful. I'm gonna give you my applauses, my virtual applauses. Let's see. We have a question, a technical question. What do you use for dimensionality reduction? Is it PCA or?
Yeah, we did not use PCA. We used the TSNE.
Okay, TSNE.
I don't think, by the way, there was anything special there. I think you could have used just about anything for that. But I think TSNE gives you slightly cleaner results.
Fabulous. I would like to ask you a more conceptual question. So how can you imagine a technological solution for dealing with this
Yeah,
whole fakeness? Like,
yeah,
we have spell checkers. Can we have
good,
fake checkers? What would it take to get there?
good. I'm glad you asked this. Let me preface this answer, Daniela, by saying that the technology I'm about to talk about is related to work that I do with a small startup in which I have a financial interest. So I have a little bit of conflict of interest in what I'm about to describe to you, and I think it's important to mention that. So everything I've described is what falls under the category of passive forensics. You wait, you sit back and you wait for the video to hit, and then you try to figure out if it's real or not. And that works reasonably well when it's the New York Times or the Associated Press or Reuters that are willing to wait days or weeks to get it right. Or it works well in the courts of law, where you have days, weeks, months, years to get it right. But it doesn't work well on Twitter, Facebook, YouTube, and TikTok, where things move at light speed. So how do you get to what you just said? I like that analogy, by the way, the spell checker. That's exactly the right way to think about it. So the passive forensics are never going to get there, in my opinion. We're never going to have the accuracy and the speed to be able to analyze any type of image, any type of video, any type of audio at scale. It's not going to happen. So what can you do? So the work that is being done that I think can scale is so-called control capture imaging. And so here's the basic idea. It's quite simple. On this device, at the point of capture, either in hardware or software, you reach into the image and you grab all the pixels. You grab the GPS tag and you grab the date time tag and you cryptographically sign it. You take that signature and either you just attach it to the image or you put it onto a blockchain type of thing. And then any point in the future, you can authenticate the image back to the original. Yeah. So it's not a watermark. It's not, we're not inserting something into the image, which we all know has problems because those can be removed, but it's a cryptographic signature. If somebody wants to remove the signature, it's fine. You just won't be able to authenticate the image. I think that's one technique that could actually work at scale if it was on every single device. And the good news about these things is this is where, what, 99.9% of photos are taken today, right? We're all taking photos on these devices now. They're all HD cameras. I bet Ted is probably taking photos on these. So I think that technology can scale and it can work. Now, there are limitations to that. There are things to worry about. There are privacy issues to worry about. But if you think about the direction, it makes sense. It doesn't make sense for me to take a photo and send it to the world and ask everybody receiving it to fact check it. That's insane. What makes more sense is for me to take a photo, authenticate it, and then put it out to the world. So that is the technology that I think could work. But now what do you need? You need Apple and Google to build it into the devices. You need the Facebooks and the YouTubes and the TikToks and the Twitters and the social medias of the world to prioritize that content, to say we will trust content, we will prioritize trusted content over non-trusted content. And then you have to deal with a couple of very tricky issues, which is human rights watching. Like, what do you do with an investigative journalist, a whistleblower, somebody who's doing human rights to make sure that they are not somehow being exposed? And you got to figure out how to add in some anonymity to that. That technology exists today, but there's a lot of infrastructure that would have to get built around it.
Thank you, Hany. We have just a few more minutes. I want to sneak in two more questions from the audience. Can you generally tell if a picture is fake just by trying to identify pixel overlays?
By identifying pixel overlays, I'm not sure exactly what that means. So let me answer it this way. We have a number of different techniques for detecting image manipulation that work at that pixel level, that look at things like, has this been compressed more than once? Is the color filter array Bayer pattern consistent across the image? Do you see inconsistencies in the underlying image noise, for example? So the answer to that is sometimes yes, sometimes no. The problem with those really low-level pixel level detection schemes is that if somebody takes an image, HD, manipulates it, and then downsizes it by a factor of 8 and recompresses it to 75% JPEG compression, all of those artifacts disappear and you introduce all these gnarly JPEG artifacts, which make those very difficult to detect.
Hany, one last question. Do you have any thoughts about detecting fake audio or fake speech to complement the fake video?
Yeah, we've done some work on fake audio with one of my former PhD students, Sway Liu, who's now at SUNY Buffalo. It's, I have to say, I'm embarrassed to say this. I always thought that when I went to go do speech, it'd be really easy because video seems really hard and image seems hard, but not as hard as video. And I just figured as I moved down the dimensionality, it would get easier, but audio is really, really hard. We have developed some techniques. I think it's somewhat of an orphan field. Most of the people in my field don't look at audio. And I think it's really ripe for a lot of really interesting questions. So we've done a little bit. There's a few papers on my website about it. There's a little bit of a literature, but it's a little neglected in my opinion.
Hany, that was really wonderful. First of all, great to see you. Second, so excited to see the really insightful research from your group. Thirdly, I look forward to a better world where I will have the fake catching system, so I won't have to worry about fake images and fake videos. Really, thank you very much. On behalf of all of us, I'm going to give you some another round of applause. And maybe you can stay on for just a minute. Bye, everyone. See you next week.
Thanks, everybody.